binary operation table. We have binary operation table or multiplication table or composition table or that much all. So we'll see this. See, this is actually a visual representation of a set under some binary operation, and in this table we will have every result. When you will operate two elements under some binary operation, the result you will get, we will see in this table. We will have all results in the table. Let us see, suppose, and this table is only for finite sets. Set must be finite. S be a finite set, and star be a binary operation, obviously on S, and this table has a format. So basic format for this table is, we have one header in row and in column, and in this position we have our operation, and here we have all elements of the set S. Here we have elements of S. Also in column we have elements of set S in any random order, and in entry in, this is a note, in this star is not same as this star. This is my binary operation, and this is I am using to note something, the bullet point. In row of X, suppose we have elements of this set S here. Suppose somewhere we have X, and column of Y, somewhere we have Y, in row of X and column of Y, row X, this is row X, this is row of X and row of X, and this is my column of X, this entry is X star Y. In row of X and column of X, Y, we have entry, we have X star Y. This is X. So this is the basic format. So in any entry, suppose this is one entry, and here we have, suppose this element is A and this element is B, we will have A star B. First one is from row, second one is from column. Remember that. So this is our basic format. I will see examples. Let me erase it. Pause the video to note. Let me make an example here. Suppose example. Suppose we have set, our set is S. Let me make it colorful set. Our set, and the set contains 1 minus 1 I, complex I, whose square is -1, and minus I. We have operation is complex multiplication and I can use multiplication symbol. Let us write the binary operation table for the set with the binary operation complex multiplication. So we have one row, column. In here we have our binary operation. Here we have elements 1 minus 1 I minus I, 1 minus 1 I minus I, let me separate them. So here we will have 1 times 1 times complex multiplication with minus 1 1 with I, complex multiplication I, 1 with minus I will have minus I, minus 1 with 1 minus 1 times minus 1, complex multiplication 1 minus 1 with I, minus I, minus 1 with minus I minus I times I, complex multiplication I times I is minus 1, I times minus I plus 1, minus I 1, minus I, this is plus I, this is minus I square is minus 1, we have one more minus 1, so it is plus 1, minus I, minus is plus, I times I, which is minus 1. So this is our operation table, or binary operation table, multiplication table, or composition table of this set with our operation complex multiplication. So let me erase this one now. Let us have the example section. We will use that. Here we have some observations. First one. Suppose in this operation table I have one element which is outsider. Let us make a coronavirus symbol. Coronavirus. This is one outsider. Outsider means this is not in our set. Not in our set. Suppose some entry of this table is not in our set, then the operation we are actually using, that is not a binary operation, or that operation is not closed, because binary operation on some set will give the results, the products, the outputs you will get, that will be also in the set. So if you are getting something which is not in your set, then the operation you are using, that is not a binary operation. So if something is outside or not in your set, then the operation. Suppose this one is star, then star is not a binary operation. Binary operation. Note it down. Star is not a binary operation. If you have some outsider. Second, suppose these are called elements of the set, and these are also called headers. These are headers, and these are also headers. Headers means they are the representative of columns or rows. These are headers, representatives. Suppose in some row, suppose this is one row, and the elements here are same as, this is the exact copy of the header. Suppose we are having some row, so this row is the exact copy of this header. That means suppose I have element A here, then in this column we have A, and suppose element is star here, and we have star here, or flower, and we have a beautiful little flower element here. This row is exact copy of this one, and so this one, this column, this column is the exact copy of the headers in our column. This is exact copy. Let me exact copy. This one is same as this one, and this column is same as. These are exact copies. This column is same as this column, the header column, and this row is the exact copy of the headers. Then this column has one header, suppose this one, this element, and this row correspond to some element, and if these two elements are same, then we have this element as identity. Actually what happens, let us see, if this is the exact copy of this one, this element is, suppose this element is, I am writing E, exact copy, this column is exact copy of this one. So here I will have, this is E, element is E. See what happens, this one is exact copy of this one. Here we have E, and suppose this one is X. So in this column, here we have X, and by the operation table, what is this element? This element is actually E star, is E star X, and we have E star X is same as X. So by left side we are having, this is a possible candidate for identity, and it happens for every element in right side, and we have left side E, and on right side we have, this one is E, so right we will have E, and here we have, suppose Y, this is Y star E, and if this is the exact copy of this one, so this one is same as Y, so E is our identity. So if we have one exact copy of header in the row and in the column, and we will check the headers. If these headers are same, then that element will act as identity. For example, here we have, see, 1 minus 1 I minus I, this is 1 minus 1 I minus I, and this row is the exact copy of headers, and this one is same as this one is same as this one. 1 minus 1 I minus I, 1 minus 1 I minus I, this is same as this one, and this is for the header 1 and this one is for 1. So these two are equal, therefore 1 will be identity. Observation is on inverses, and we will search for inverses if on the first hand we have identity. Suppose we have identity, suppose star is our identity, and we are finding the inverse of this happy little element, this happy little flower. In this row, I will first search where the entry star is. If somewhere I have star, suppose here I have star, then the element here, suppose here we have the cute little leaf. So this one is this happy little element operated with operation star with our cute little leaf. So this one is star. So this is a possible candidate for inverse of this element. Now what we have to do? We have to also check the other way. Here somewhere we have our happy little element, happy little flower, and somewhere we have this cute little green leaf, and in this row, this column, I'll check if this is star or not. If this is star, then this is the inverse of this happy little flower, because this one happy little leaf with our happy little flower, and in both cases we are finding identity. If this is the case, then this is the inverse of this one, and other way this is also the inverse of this one. Here let us check. So 1 is the identity, 1 is the identity element here. Suppose we are finding the identity of I. We will check where 1 in this row. Here we have 1. So this is a possible candidate. Which one? Minus I is a possible candidate for inverse of I. And in other way I'll see minus I and I. This is also 1. So inverse of I is minus I. So this is the way to find inverse of any element from operation table prior to the condition that we have identity. Now let me erase this. We have commutativity. So from the operation table, you can check the operation is indeed a binary operation or not. Second one is we can find identity if there is one, and after that, if identity is there, I can find inverses if exist. Then we can also check commutativity property. What is the procedure? Check the operation table. This is our main diagonal. This is our main diagonal. If this main diagonal is acting as mirror, this is acting as mirror, that means the elements here are the mirror image of elements here. So if I will reflect the elements, they are same. So in precisely I can say elements or the table is symmetric. Table is symmetric about main diagonal. Now let us check here. And this is our main diagonal, and this is symmetric. Also you can say this table, or if you will treat this one as a matrix, and this is a symmetric matrix. Minus 1, minus 1, the elements are symmetric here. This table is symmetric. This is main diagonal, I, minus I, minus I, minus I. So from table we can find identity. If identity is there, we can find inverses if exist, and we can check whether a set under a binary operation is commutative or not. To show a group, a set under binary operation, a group, I have one axiom associativity. From this operation table, I can't show associativity. For other things, for closure, identity and inverses, I can see the group operation, the operation table, the composition table, and this example, this 1 minus I minus 1 I minus I under complex multiplication is a group, because associativity will hold here, because complex multiplication is associative, and I have already said associativity is a rule. If that rule is for a bigger set, then that rule also will satisfy for smaller set. S is a subset of the whole complex set, so associativity will hold. We have identity, we have inverses, and this is moreover commutative. So this set under this operation is an abelian group. So this one is an abelian group. Abelian group. And from operation table I can check identity, inverse and closure property. For associativity I have to work extra. And when we are creating the operation table of a group, suppose G is a group under binary operation star, it is a group, it is given it is a group, then its operation table, the operation table that I will get, operation table is also called Cayley table in the honor of mathematician Arthur Cayley. If this set under the binary operation forms a group, that table is known as Cayley table. Thank you. Don't forget to comment your doubts. I will rectify them. I will try to cover them in our videos.